Hello. Hmm. Right. Which pen I meant to use? Um. Oh, yeah, that was quick. 3 to 9. Okay, that's a lot. We are mainly doing some chemistry because that is what most people did over the weekend. As I say, this month is a little bit funny because the GCSE people attend on a Friday, were still doing biology at that point. So a little bit confusing. But if you did do some biology, then you can ask some questions on that later. But it will be chemistry stuff. Everybody in Key Stage 3 did a topic called neutralization, which was all to do with acids and alkalis and universal indicator. Um, and stuff. Now, there is one aspect of this, because I haven't looked through these homeworks, there is one aspect of this that some of you are almost certainly going to ask me about, because it might not have come up in the lesson just because of time. And it's to do with a practical experiment in this. Now, I suspect it will come up, but if not, then, well, when it does, we will go through it. But I will go through that practical experiment anyway. Um, so I will start with questions that have been asked so far, which is I will go to the year 9 one first. There will be a bit of overlap, only because there's one of those. So I will begin with that. So, but if you have any others, then please feel free to ask. Any other concerns or questions? Um, yeah, so in terms of these sessions, by the way, they can only start at about 7:15, by the way, just so you know. So if you are on at 7, I think the email does say 7:15 actually now. Mainly because I have another lesson that finishes at 7 o'clock. So it's very difficult to zap straight onto another one. Um, so the questions. Question 4 on this one. There's been a question that's been asked. Right, is it to do with this? Sure, we can talk about it. Um, Right. Many sea creatures have shells containing calcium carbonate. Here we go. Crabs and whelks and scallops. The question says, the seas are becoming more acidic. The reason, just go off topic slightly, the reason the seas are becoming more acidic is partly to do with something called acid rain, which is produced when we burn, which is produced as a result of sulfur dioxide, which is produced by burning some types of coal that leads to that. But what is the effect of the acid on the shells of some sea creatures? Well, just a reminder when you ask a question, if you could just refer to which booklet you're doing, because that question B1, I'm not sure what that means. Question 2, B1, is that on booklet? Is that on booklet? That'll be booklet 1, won't it? Right, anyway, the answer to this question. What we need to say is when there is acid in the seawater, it will react with the shells. We need to make sure we say the word react here. That is what happens when the acid touches the shells. And what do you think will happen to the shells then? They will probably get a bit thinner or get worn away. So something like that would be what you want to write here. So the best word is that the shell gets eroded. Eroded is a geography term really in terms of things wearing away, like rocks get eroded. But if you say it wears away or it dissolves or it gets a bit thinner, something like that would be fine. You can't say it's weakened or broken down because I think that's not precise enough. Um, you did neutralization booklet 1 in step 6. Yes, correct. Um, that's what you should have done at the weekend. Yeah. Okay, so that's that part. I assume you want all of the parts of this question. A student investigated the effect of heating calcium carbonate. Here is the symbol equation. You have to write the word equation. Well, that's calcium carbonate. So that word just needs to go there. This is calcium and oxygen joined together, which is calcium oxide. That covers that. Then, right, it's a really easy question, this actually, if you understand how chemistry works, which is that if I start with, let's say, 20 grams of this stuff on one side of the arrow, then everything on the other side of the arrow also has to add up to 20 because we use the same things to make the other things, right? So if I start with 20 grams of something, I have to finish with 20 grams of it. So for example, if that was 12, for example, then this would be 8 because it has to add up to whatever's on the left-hand side. What they're telling you in this question is that 50 grams of this produced 28 grams of this. The question is, how much of this was produced? And these two numbers just need to add up to 50. So that's got to be 22, right? That adds up to 50. That's all we wanted to say there. When carbon dioxide passes through a solution, the solution becomes cloudy. This is again one of these questions that goes off into different areas that we don't necessarily cover in the lesson yet. But there is a test for carbon dioxide which involves a solution called lime water. And when you put carbon dioxide gas through this lime water, which is a clear liquid like water, then you end up with that liquid becoming a bit sort of cloudy or white. So that's what you're meant to know for this question. And then what have we got here? Oh, that's question 5. So that's done. Right. Okay. I will move over to there's one question from the booklet before. I'm sorry, I do this in a very random order. I just try to be as efficient as possible. So, in the Year 8 booklet, there is a question that says 5 part 2. That must be this one, I guess. I'm guessing. I don't know. Do you want to be more precise about that? So someone said 5-2, Year 8. And I assume that means booklet 2, just to be clear. Don't put the year number if you have the booklet number, just to be precise about it. This should be booklet 2. Yeah. Hmm. 5. Don't see a part 2 apart from this one. Use the results to arrange A, B, C, D in order of increasing strength. Well, I think all you do here, decreasing acid strength. So I think you just put it in order of the pHs, right? The strongest acid is that one. So that's presumably C, most acidic. And then it goes to D, which is a bit less acidic. No, sorry, A, which is a bit less acidic. Then D, and then B. So C, A, D, B should be the answer to that question. I'm not going to check it. Well, I'm assuming that is the answer to that question. Right, so I'm going to move on to question 7, booklet 3. I didn't ask that before. Let me see what it is. Okay. Right, yeah, I'll just do this quite quickly. Good question. Right. The question says here, copper sulfate is made by reacting copper oxide with an acid. Now, in your studies, there are basically only ever 3 acids you will come across. They are called hydrochloric acid, sulfuric acid, and nitric acid. Now, with each of these acids, when you react them with something, then you know what the ending is of the product. So when you react something with hydrochloric acid, you make something chloride. When you react something with nitric acid, you make something nitrate. When you react something with sulfuric acid, you make something sulfate. So when the question says we made copper sulfate, you know that the only acid that it could be is sulfuric acid. That's what that means. Um, So, just to be clear, the question who is being asked about neutralization booklet 1, the way these we are doing that booklet. I am guided by your questions on it. So if you say on that booklet, I didn't understand question 3, then I will pull it up in a moment and go through that one. Here is booklet 1. It's ready to go, just to be clear. I just do 3 together during this session, depending on which one you have. So just need to ask me the question that you need help with. A balance symbol equation for this reaction. So we reacted copper oxide, that's CuO, with an acid, sulfuric acid. Again, this is quite a difficult question if you don't know it, but it is H2SO4. We produced copper sulfate, which is there. Now, because this is a neutralization reaction, whether we've got like an acid and an alkali, we always get water at the end. So that is the symbol equation. Oh God, they want balanced and state symbols. All right, copper oxide is a solid. That an acid is always aqueous. Copper sulfate is always aqueous, and water is always a liquid. So that's your state symbols. Is it balanced? Yes, it is already balanced. So that's it. That would be the answer to that question. Right. Let me see where I am. Right. I'm going to. So booklet two, question 5C, booklet two. Sorry, I know I'm skipping booklet one at the moment. I'm getting there because there's a lot of questions on there. Um, 5 part question. Booklet two, 5 part 2. Yeah, I don't know what that means. Is that this one here? A solution with more hydrogen ions and hydroxide ions is acidic. I think I've done that. 5C, booklet two. That's here, is it? Citric acid is a weak acid. The word weak means that the acid is partially ionized in water. That is what we want to be able to say for a weak acid. Whereas a strong acid, we say it is fully ionized in water. That's quite a technical question, but it's very easy to remember the answer because it is always the same. That was that one done. Right, I think that's more or less. I want to skip over to question one if anybody has questions from their other booklets and tell me. But let me go through this. So we've asked question two and then three. So that's basically the whole booklet here. So, which I understand because for you guys, this is not going to be straightforward. Right. Um, Paul had 4 substances: citric acid, copper sulfate, indigestion tablet, and sugar. He dissolved 1 gram of each substance in some water and used universal indicator to find the pH. What happened? Sugar solution does not change the color of green universal indicator. What does it tell you about sugar solution? Well, green on universal indicator means it is neutral. That is what um, that means. Um, Suggest the pH of citric acid. Remember, on the pH scale, we have like 0 at one end, 14 on the other end, and 7 in the middle. An acid is anything that's less than 7, basically. That is an acid. Anything that's more than 7 is an alkali. And then if it's exactly 7, it is neutral. So if I've got citric acid, then we just need to say a number that is less than 7. So 3 or 4 or 5 or 6 or 1 or 0. Any of those would be sufficient. Um, Booklet 2, 5 part 2. Again, I thought I'd done that. So yeah, let me go back to that. I don't know what 5 part 2 means because I've done 5 part 2 here, did that, and part 2 here. So I need to be more precise as to what your question is. And then 5E part 2. I did that, didn't I? Done that as well. Yeah, fine. Okay, so we've done that. 3, 5, yeah. So for booklet 1, and again, the person who's asked the last questions, make sure you say which booklet. I know it's booklet 1, but if you only do it, just make sure that you say booklet 1 so that I switch over to the right place. Right, I'm doing most of booklet 1, so you don't have to worry about that. Indigestion tablets neutralize acid in the stomach. What do we know about neutralization? We know that if we add an acid to an alkali, it becomes neutral. And so, if these tablets neutralize an acid, then they must be an alkali. So that is all of that. Um, then let's have a look at, we've got one of these weird flow charts here. Complete the flow chart below with the names of substances in the box. Okay. Does the substance dissolve in water um, to form a blue solution? Okay. We'll come back to that because it's not obvious, but the other ones I think are obvious. So does it turn universal indicator red? Universal indicator red means that we would need an acid in this position here, because that's what universal indicator turns to in an acid. The only acid from this list is citric acid. Okay, does it turn universal indicator blue? Blue would be an alkali if it does that. So we need an alkali over here. We already know an alkali from this list because it was in the other question, the indigestion tablet. And then the other two are less obvious, but I'll tell you what the answer is. Copper sulfate is a particular thing that once you do a bit more chemistry, you will know that it turns blue when you put it into water. So this is the copper sulfate. which means that the only other one that we've not mentioned so far is sugar, because sugar is neutral, remember. So we know that it doesn't turn anything, change the universal indicator's color. Um, the person who mentioned the year 11 booklet, again, I need more specific. Tell me, get ready for the next hour in terms of specific questions um, from what you did. And I think you will have done, well, you have to tell me which booklet it is, which subject it is as well, because it's different. So we'll sort it out in the next hour, don't worry. Question three, booklet three, I'm not doing that just yet. So continue with booklet one. Um, so someone basically has 3 to 9, which would cover it's basically the whole booklet, which will cover everything. Again, if you're going to ask a question, please make sure you say the booklet number. Um, because otherwise I have to guess. Right, booklet two again. I want to come to that later now. I want to get through this booklet first. So, question three gives you loads of. Oh, I remember doing this with people. The diagram shows a key. So you'll see these quite a lot in these questions where they give you like all of this little bits of information. You've got to use it to answer questions. It is quite easy. It's like following a map. Okay, so use the key to identify chemicals A, B, and C. So chemical A is a white powder. So is the chemical green? No, because it's a white powder, right? So we're going to follow this path. It fizzes when dilute hydrochloric acid is added. When dilute hydrochloric acid, does it fizz? Yes, it did fizz. So we're now here. It dissolves in cold water. Does the chemical dissolve in cold water? Yes. So we're here. That's it. That's all you had to say. Um, chemical B is a green powder. So we start at the beginning. Is it green? Yes. It does not fizz. Does it fizz? No. Which means it is this one here, nickel sulfate. You're just following the path. Got one more. Chemical C is a white powder. So no, it's not green. It does not fizz. No. It is insoluble. Insoluble means it does not dissolve in cold water, which takes us to there. So it's calcium sulfate. And we're done with all of that. We've got more questions coming up. Help on year 7, 8B. Yes, we're coming to, I'm just getting through this whole thing and we will get there. Nickel carbonate is green. It is the nickel that makes nickel carbonate green, not the carbonate. How do you know that this is true? Well, so, and it's to do with this. Okay, so is the chemical green? Nickel carbonate is green. But I've got other carbonates here as well that were not green. Okay, which tells me that just being a carbonate does not make it green. You see what I mean? So the carbonates here, but these were not green. No, they were not green. So that tells me that the carbonate isn't what makes it green. And also, these two chemicals both have nickel in and they're both green. So the way you answer this question is you explain that um, these other carbonates, sodium carbonate and calcium carbonate, are not green. Which proves that it's not the carbonate that makes it green. And also, you can say that nickel sulfate is green, which is enough proof that it's the nickel that's making it green. Okay, right. pH paper is used to show whether acid is. Okay, that's fine. It gives you some information here about colors and pH. Um, right. Some solutions were tested with pH paper. The results are below. Complete the following table. So orange juice, the color was red. So that means that, well, we know that if the pH, remember the pH scale again? 7 is neutral. Anything less than 7 is an acid. Anything more than 7 is an alkali. So if it turned red, then we know it's an acid. If it turned blue, we know it's an alkali because it's more than 7. If it turned purple, we know it's an alkali because we know it's more than 7. If it turned yellow, we know it's acidic. And that's covers that. Got more questions here. Um, um, What is an indigestion tablet? Like, what is the substance chemical formula? Well, it depends. There's no chemical formula for an indigestion tablet. It's got lots of things in it, lots of chemicals, like it'll be calcium carbonate, for example. Um, but the point is, it is an alkali, and there's lots of different chemicals that make it an alkali. But that will be one of the things in it. So there's no formula for a indigestion tablet other than to say it is an alkali, because all it does is it helps you get rid of some acid, like when you have heartburn, when you get some acid, when it gets rid of it. Which substance was the most alkaline? Most alkaline is the biggest pH, so the closest to 14. So the oven cleaner, I guess, the most alkaline. Equal amounts of egg white and milk are mixed. What is the most likely pH? Oh God. Egg white and milk. So egg white was a pH of like 8 to 10. Milk was pH 6. So when you mix these together, you should probably get something in the middle. Um, so I would probably go with pH 7 out of all of those options, I would say. Okay. Um, Right, I'll keep going. Give the names of two fossil fuels. The three fossil fuels that you should know of, and it should have come up in your verbal test, if any of you, for those of you that did it, are coal, oil, and gas. So any two of those into these spaces would be sufficient. Um, when you mix sulfur and oxygen together, you get something called sulfur. You can say sulfur oxide or you can say sulfur dioxide. Either way, it is fine, I think, for the answer to that question. And then I remember I mentioned this question to some people when I taught them that there was a picture of a helicopter going over a lake somewhere, um, which was, and it says that there's some acid rain has collected in this lake and they're dropping something called calcium hydroxide into the lake. Well, the reason we do this is because we don't like this being acidic, because it's not good for the fish and plants and stuff that live in there. And so, how do we get rid of an acid? We add an alkali. That must be what this is, right? Um, and the question is, what effect does alkali have on the pH of an acid lake? Remember, if it's an acid, its pH has dropped below 7, and we're trying to bring it back up. So it's going to increase it. Okay, that's what it's going to do. Um, What is the product when calcium carbonate reacts with hydrochloric acid? The answer to that question specifically is calcium chloride, carbon dioxide, and water. Um, right, when calcium hydroxide reacts with sulfuric acid in the lake, a calcium salt is formed. What is the name of this? So again, for the people that I taught, we should have done quite a lot of this. When you react a metal with anything, it doesn't matter, with sulfuric acid, you will get something sulfate. That's the ending of the product. So you take this and you put that on the end of it, which means that that is the answer. Here is a tree damaged by acid rain. The trees have lost their leaves and died. Why are leaves needed for a tree to grow? Suddenly we are switching towards some biology all of a sudden. Well, I think an answer involving photosynthesis should probably be all right. Um, so, for example, you just mentioned that that is how a tree or a plant carries out a process called photosynthesis. Leaves are needed for that because they're green, they contain the chlorophyll, and that is what. What effect does acid rain have on buildings made from limestone? Again, what you can say is like a bit like that shells question that we saw earlier. You can say that the acid rain reacts with the stone. And then you could say more, it erodes it away, but it's only one mark, so I wouldn't say too much more than that. Um, Right, I will just to satisfy people switch over briefly to a question from a couple of the other booklets. I will come back to this. Don't worry, we have time, so don't worry. Um, Let me work backwards here. Question 6 on this booklet. What happens when an acid reacts with an alkali? I think what you need to explain is that the H plus ions in the acid, because that's what an acid is made of, remember? What makes something an acid is these things called H plus ions. What makes something an alkali is these things called OH minus ions. So H plus ions in the acid react with the OH minus ions in the alkali to form H2O, water, neutral. That is what happens. Right, that's that one done. Yep, I'll get back to the year seven one, don't worry. I'll do that once. I'm not doing any more questions from the other booklets now, so I have enough time to ask. To 7A. I mean, really, you want me to answer this question 7A? Well, firstly, the what you have to do to answer this question is add up these numbers in milligrams. So that would be what number goes there. Okay, so just add up these four. Shall I do it? 10, 800 milligrams, seems to be. Now, in grams, there are 1,000 milligrams in a gram. So what you do is you divide this number by 1,000 and you should get 0.8 grams. I'm hoping that's the answer to the question. I suspect it is. Um, yeah, I'm not doing any more questions from that. Again, what I need you to do in future is ask these questions at the very beginning, because again, I'm not inviting you to do the homework live while I'm doing it. So question three, before three. See if I've already done that. Um, right. I'll do this one. So again, I've sort of actually I've already answered this question. I explained that the way you get these endings on a chemical, this ending comes from nitric acid. This ending comes from sulfuric acid. So we already know the answer to this question because the question is which acid reacts to form ammonium nitrate? It has to be nitric acid. Okay. Um, and then we already know this one because I just told you which acid reacts to ammonium sulfate. It has to be sulfuric acid. Okay. There's only three options here. Um, and then exothermic means heat is given off. Okay, fine. Right, that's that done. Let's see if I've already done that. Yeah, no, not gonna do that now. Um, I might come back to that if you want to stick around. I just want to get through the earlier booklet. So, question 3 to 9, and then Jenna, you asked 8 to B. So, right, 3 to 9. I just need to get through the next three questions here. The pH scale below is used to measure how acidic or alkaline a solution is. Okay, we know this. The graph shows how the pH of the liquid in Barry's mouth, where'd that come from, changed as he ate a meal. Use the graph to give the pH of liquid in Barry's mouth before he started to eat, which is there, before he started to eat, so 7. What does this pH tell you about the liquid in Barry's mouth before he started to eat? It must be neutral. We know that pH 7 is neutral. Um, and then what happened to the pH as he ate the meal? What's happening here to the pH? It's decreasing. Okay. And then he chews a special chewing gum. The chewing gum neutralizes the liquid in his mouth. What type of substance neutralizes an acid? Come on, we know an acid and an alkali makes neutral. Um, right. Question 7. Um, just on a general note, the last person who asked any questions, 9E booklet 2, the one person that just asked. Again, what I need you to do is return with with provide a name if possible. Otherwise, I won't do that question. Um, we boiled some red cabbage in water. The cabbage water turned purple. We separated pieces of cabbage from the cabbage water. What method do we use? If I had some pasta and I have some pasta cooked in some water, then at some point you drain that water out by putting it into like a sieve, it's called. That separates the solid pasta pieces from the liquid. That process is called filtration. When you get rid of solid pieces from a liquid, it is called filtration. What if it was OH plus ions? No, because there's no such thing as an OH plus ion. There's OH minus ions or there's H plus ions. It is one or the other. Um, yes, so the person who just asked 9 and E, could you just confirm what your name is, please, so that I can relay some information back to your parents? That'd be great. Um, why does it keep changing the name then? Anyway, we'll see. Um, Jam wanted to find out if the purple card will contain more than one colored substance. So again, you may not know this, but I'll tell you because we'll do it later. There's a thing called chromatography that you will do soon enough, where you get like an ink and it separates into different colors. So that's how we deal with questions like that. Has that covered most people? And then uh, we mixed the purple cabbage water with some other liquid. She wrote the colors of the mixture in a table as shown below. The mixture turned blue. What does this tell you about the washing up liquid? So I think this whole cabbage water situation is just used like universal indicator, I hope. Oh no, it tells you here. So we know the information from this table. Um, if it turned blue, we know that it's an alkali. That's it. Let me try that down. What color was the mixture if it was acidic? Red. That's it. You just read off the table for that question. What is the name of a chemical which changes color when it's mixed with acids or alkalis? It is called an indicator, like universal indicator. These things change color. Um, okay. And then it's got a couple more to do, which is, and then I'm going to stop at the end of question 9 because nobody has asked more beyond question 9 in this booklet, I believe. Um, so, question 8. Bees and wasps are both insects would use a sting as part of their defense. The pH value of their sting is shown. You see, that's pH 2 for a bee, wasp is pH 10. That is acidic, that is an alkali. Complete the table to show whether the stings are acidic or alkali and what color those. So, a bee sting, pH 2, is an acid. The color of universal indicator is red in the presence of an acid. The wasp sting is pH 10. If it's more than 7, it's an alkali. And the color of the paper, you can put blue or purple. I think you should be fine with either of those. Um, this shows the pH of some household substances like toothpaste. Right, give the name of one substance which would neutralize each sting. Right, a bee sting is, as we just demonstrated, an acid. How do you neutralize an acid? You use something that's an alkali. So you need to use something that has a pH that's more than 7, like this one, or this one. So either of those two are answers to that question. But for the wasp sting, because the wasp sting is an alkali, if you want to get rid of the alkali or neutralize it, you need something acidic to get rid of it. So anything with a pH less than 7, like vinegar or lemon juice, we would need for the wasp sting. It's interesting. Um, and the last question on here. Joanne added iron filings to copper sulfate solution, and they observed what evidence shows that a reaction has taken place. What has changed from here to here? Well, the color has changed. That was blue, and then now it's green. A color change suggests a chemical reaction has happened. Um, the reaction in iron and copper sulfate is a displacement reaction. Give the name of the orange metal visible after 1 week. I'll just tell you what happens. A displacement reaction is one where one metal kicks out another metal. So the iron kicks out the copper, taking its place, and it becomes iron sulfate, and the copper gets separated out, and copper is orange, essentially. So the name of the orange metal is copper. What is the name of the compound? That would be iron sulfate that goes over here. Joanne poured the green solution into another test tube. She added some copper pieces. What will a displacement occur? Um, and I'll tell you the answer. This is quite complicated. The answer is no, because a displacement reaction only happens when a more reactive metal kicks out a less reactive metal, which if we try and do it in reverse, it won't happen because copper is now the less reactive metal and it doesn't kick out a more reactive metal than iron. That will do. Um, which two metals would react with aluminium nitrate in a displacement reaction? So if I've got aluminium, the only way to displace it is to use something more reactive than it. So any of those three should be fine. So you just find them. Calcium, potassium are the only two options that are above aluminium in that table. Right. Right, that covers that, which means that I can just drift back lastly to this question here, which is the very last question on this one, which seems to be challenging people a little bit. I think that should be sufficient for everybody in the question that you've asked. If I've missed something, then tell me. But this question here. This shows the solubility. Solubility means how easy it is to dissolve of three solids in water at room temperature. So this stuff, this much of it will dissolve in this much water. This much stuff, quite a lot more of it will dissolve in water. This stuff does not dissolve in water, basically. Um, so we've got three solids A, B, and C, and then gave to the information table two, and then now we've got table two here. So we've got three solids A, B, and C. Well, firstly, we need to figure out what A, B, and C are. Now, isn't C definitely this one? Because we already know this one does not dissolve in water, and when they added this stuff to water, the solid does not dissolve. So C is silicon dioxide because it did not dissolve in water. That's the first thing. That's the easy bit to get. And then the harder bit is understanding which one's an acid and which one's an alkali. So out of these two, generally, I should just tell you that hydroxides tend to be alkalis. So sodium hydroxide uh, is the alkali, and that must be A because the pH is 14. That makes it an alkali. So A is an alkali because it's got a pH of 14, which means it must be sodium hydroxide. I might not be fully answering this question, but I think that's enough. And then that leaves you with the one that's left, which is B. B must be phosphorus oxide. And that should be enough. So I think you just have to name the correct ones and say why. I'll just have a look at the answer to that just to make sure I'm not telling you everything wrong. Oh, also, actually, I forgot to do this. You must use an indicator in this method. So you want to say that you would add universal indicator to each solution. That actually makes it much easier. If you add universal indicator, then if it turns purple, then it's a strong alkali, which means it has to be. Oh, wait, actually, let me work this out. Yeah, then so that's sodium hydroxide. It's the alkali. Um, and then you could put it into if it turns red, then it's solid B, which we just said is phosphorus. That'll be red in universal indicator. And I think that's enough. You don't need all of the points in this question. Um, um, well, in answer to the last question about don't you have to write about required practical, this question is a key stage three question, and it is slightly simpler. So we haven't quite reached required practical stage yet with regard to this question, just so you know. Um, and then, okay, I've got one more then, 10C. Let me have a look at what 10C says. Oh, passed it. Um, so question 10, we've got the person doing some stuff with universal indicator. That should be okay. Michelle measures the pH of some milk. Ooh, so write the God. Well, write the axis label for the graph for X. If you read the question carefully, we measured the pH for 5 days, and there seems to be a scale that goes 1, 2, 3, 4, 5. So surely that is just days, right? That's got to be days. So each day you've measured it and then recorded it on the graph. How does the pH milk change over 5 days? What's happened to this graph? It has decreased, and that is enough for that. Um, I think I have hopefully covered everybody's requirements in that session. I will stop at this point, and then we will do what the GCSE students had. And again, this will be a little bit complicated because if you attended on a Thursday or a Friday, you did some biology, and if you did beyond that, you did chemistry, just because of the way our schedule is. But I have got everything ready, so I can answer everything over the course of the next hour. So I will return in 5 minutes and go through any questions that you have from year 10 and year 11, which are a bit more complicated questions. I shall be back. Um, and I'll have a look at that math question in the meantime. Yes. Oh, God, I hope. See how complicated this is. Ooh. Right, anyway, I'll be back in a few minutes. Hello. Right, I've been asked some questions, so I'm going to do that first. I presume that is a chemistry question. If you just specify, just in case. Most people did chemistry, but some people will have done biology, depending on what day they come. So I just want to make sure I cover everybody. Okay. So, year 10, question 8A, and question 1 and 2 that are at the end of the booklet. Okay, fine. We close this. This one. A student was trying to produce hydrogen gas. This is the apparatus they use. So they reacted some copper with hydrochloric acid. And you should technically know that when you react a metal with any acid, then one of the products is hydrogen. Um, but this time, no gas was produced. A student teacher said this was because the substance in the flask did not react. Why might that have been? Could be to do with temperature. Um, but better answer is the substances in the flask did not react. So dilute hydrochloric acid and copper. Um, phew, I'm not sure how you would do that, but the answer to the question here, the only answer to the question that makes sense, is that if you're trying to produce hydrogen gas. See, I would have said something else to the mark scheme, but the mark scheme says that copper, in this case, the copper is unreactive. Copper is actually the least reactive on the reactivity series. It's right near the bottom. Um, so actually, if you just wrote that, then that is sufficient for that question. It's a suggestion, isn't it? So it doesn't mean that it wouldn't have happened. It's just what might you get. And then, yes, I will get to that biology homework. Yes, don't worry, 1C and D. And I might even have done it, so you'll just have the answer straight away. So I'll have done it last week, probably. Um, that's question 10, 8, question 10, question 8A, and question 1 or 2 at the end of the booklet. Um, Oof, I've not seen these ones. Let's have a look at how complicated these are. Um, right. Oof. A student carried out an investigation to determine the order of reactivity. It's a very common question, this whole like order of reactivity stuff, where they ask you stuff like that. I will come back to 7C in a second. Is that 7C at the end? Is it at the end? Is there a 7C? No, it's not. It's way earlier on. Yeah, I know the ordering of questions is awkward here. Right. So a student carried out an investigation into the order of reactivity. They added to the hydrochloric acid and repeated it. Right. So, based on this, what looks like the least reactive? So we've got bubbles formed quickly with some metal remaining. Few bubbles were seen. Bubbles formed quickly. Bubbles formed very quickly. Right. So a few bubbles were seen. That seems like the least reactive so far, right, out of all of those. So I'm going to put that first. Then um, bubbles formed quickly and bubbles formed quickly. Well, formed very quickly to me suggests that goes to the end. Okay, because the only one with the word very in it. Um, and then we just got to figure out what goes in the middle. So because in Y all of it had reacted and in W some of it hadn't because it was still remaining, that suggests that Y is more reactive than W. So I'm going to put Y there and W there, and that is the answer. Um, then they repeated it using an excess of sulfuric acid in place of the hydrochloric acid. Hydrochloric, sulfuric, slightly different. Um, and then they've written down the word equation here. When metal Y reacts with dilute sulfuric acid, bubbles formed quickly at first, and then it stopped. Most of it remains. Explain why the reaction between metal Y and sulfuric acid stopped, even though there was solid metal Y left. Well, let me have a think about this. Um, That's quite a difficult question, but it relates to an understanding of something called iron sulfate, which is partly to do with rusting, and the only reason a reaction with a metal would stop, right, is if for some reason there's like a barrier that stops the acid getting to the metal. And so what you're supposed to say, which I think is really hard, but the this stuff here, the metal sulfate, um, forms a barrier, and therefore it stops any of the acid reacting anymore with it. So it prevents further reaction of the metal. So the acid is here, but it now can't reach the metal, so it kind of all stops because there's something in the way. It prevents a further reaction of the metal with the acid. Explain the meaning of the term weak acid. You basically always need to say that it, whenever you get a question about a weak acid or a strong acid, for a weak acid, you always just need to say that it partly ionizes in water. Whereas if it was a strong acid, you say it fully ionizes in water. If it only partly ionizes in water, it means that you have fewer H plus ions, and they are the things that make it acidic. The more H plus ions you've got, the more acidic it is. So if there's fewer, it is less acidic, essentially. Um, so I'm just going to go through these end questions are quite challenging, so I'm just going to go through this first. A student investigated with different metals with hydrochloric acid. Okay. We repeat the experiment with different metals, repeat the experiment 3 times for each metal, and measure the temperature change. Okay. One of the results is anomalous. Put a ring around it. Well, you just need to look at these and see which one's significantly different from the others. See, they're quite close together. They're quite close together. But with the zinc, this seems quite a way off to me. So that would be the anomalous result. Calculate the mean temperature for magnesium. We should be able to do this. Add these 3 numbers up and divide by 3. Okay, so I'm not going to do that, but that's how you calculate the mean from some numbers. If you want to improve to get more accurate results, what could you do? I'm going to have a look at what we did. Well, whenever you do an experiment with temperature change, one of the things you should make sure you look out for is this, which they've done. If you use a glass beaker, it's not great because it conducts the heat out of it and the thermometer won't pick it up. The other thing that you should look out for is having a lid. Um, oh, sorry, I missed out a question, didn't I? It was the reason. Oh, yeah, the reason. The reason for the anomalous result could be because you just measured it properly. You made an error taking the temperature. That is perfectly fine as an answer, like an error. Um, You could also say that the reaction didn't finish, and that's why you got a smaller temperature change. It could be for some reason it didn't finish. But the answer to this question about what you could improve is pretty much always, if you've got a temperature question, just make sure there's a lid on it. So you put a lid on it, or you could even mention a digital thermometer, because that doesn't look like a digital thermometer to me, but lid. And what the lid does is it prevents heat loss through the top. Okay. Okay, and you concluded that the more reactive the metal is, the higher the temperature rise. Describe further tests the student can do to confirm her conclusion. Well, it looks like um, the more reactive metals, which it doesn't make it obvious here, had a bigger temperature change. But if you want to prove it or do more, right, surely you should use more metals here. You only use 3, so it doesn't really prove that much. So I think the easiest answer to say is use a wider range of metals, or more metals would be fine. And also, you only did this reaction with one acid. You did it with hydrochloric acid. Why not try it with different acids as well? Right, because it could be that the acid makes a difference. That's all of question 7. I forgot 7 part 2, did I? Oh, I did that now, yeah, fine. Um, could we also do increase the number of times the experiment is done? Let me check. Technically, yes, but uh, you see, the question is because it says more accurate results. That the word accurate there is important because more accurate results means that, could we have done something wrong with these specific experiments? Like, could something have gone wrong? So doing it more times doesn't give us more accurate results if we're already doing something wrong. If the question had said more reliable results, then doing it more times makes it more reliable or more valid. So it's a little bit of a sketchy one, that word. So I would stick with how you improve the experiment as opposed to, or the actual thing we did rather than doing it more often for that question. Um, right, 3B and 8B. Right, I can go backward now and answer some of the earlier questions. 7C, year 10. I will come to the year 11 one ASAP. Um, but all of this is useful. 7C, presumably that's one. Um, You are given solution sodium hydroxide and ammonia of the same concentration. Describing sodium hydroxide as a stronger alkali than ammonia solution. Now, I've got lots of things in my head that I could say here. Um, but I mean, just universal indicator would be enough. So if you used universal indicator here, remember universal indicator tells you if you've got a stronger alkali or not, because with universal indicator, a strong alkali turns like purple, right? So your sodium hydroxide would turn universal indicator purple, whereas your ammonia, which is a weaker alkali, would turn it blue. So universal indicator is a good way of telling the difference in a strong and a weak alkali. That would probably be the best answer that I would go for. You'd probably say a pH probe as well for that one. Um, and then 3B and 8B. Just to confirm the year 11 question, are you asking me about chemistry? I just want to make sure that you are asking about chemistry, or is it biology? Because it depends on what day you come, and I can't remember. Um, right, so 3B and 8B I've still got to do from this. And year 10, the second question, one part two. Oh, mm. Yeah, so it's a difficult question. This, and it's possible that you don't really need to know this. It might just formed it. The question basically says, why did this reaction stop, even though we had still got, so let's say this metal that's here is reacting with this acid. Okay. Now they're reacting, but then it stops, right? But we've still got some of this left. The only way that reaction stops is if something gets in the way and stops the acid reacting with the metal. And that's essentially the answer to this question. It is quite a difficult one, which is to say, like, why did it stop? And you sort of have to guess a little bit. But the answer is that this stuff that's produced formed a barrier that was in the way. So it stopped the acid reaching the metal now. So now no reaction's happening because nothing's getting there. That was a complicated question. And then, yeah, I'll come to that year 11 chemistry one in just a moment. 3B and 8B, I'll just get these done, and then we can move on. Okay. Okay, so this is a very specific practical thing that you're meant to know, which is that it says here, blue copper sulfate go white when warmed. So if I warm this, okay, remember when you warm something, what do you think is happening? You are any water in here will evaporate. Okay, so the water evaporates. So now it turns white, okay, after warming, because the water's gone. How could you use this as a test for water? Well, if you add water back to this, what do you think? What color do you think it'll change to? Surely it will change back to blue. It is technically what's called a reversible reaction, where you can make it turn white by removing the water and then putting the water back and it turns blue. So you are supposed to say that for a test for water, what you would do is add water to the white copper sulfate and it should turn white if it's water that you are dealing with. Let me just check that is what it says. Yes, add water and it should change blue. Um, so that was that one. And then I have got another question here for 8B. Let's check what that is. Um, okay. Give the name of this apparatus. This is called a gas syringe, which is often asked in various science subjects about because we are often collecting gas and working out how much gas we've got, and that is the way you do it because it can measure the amount of gas. What are we doing here? We produce hydrogen from two substances. Okay. The data went 4 times. The results in the table below. One of the results is anomalous. That looks to me like that one. the one that's far enough away from the others. Anomalous means something's gone wrong, basically. So if that's what you get once, then that, then that. But then this looks quite far away from the others, so that would be that one. Give a reason for your choice, and I guess it's just that it's a lot lower than the other ones. All right, so that's I don't know what I've done now. 8B, yeah. Oh, sorry, I just did a question for no reason. Um, right, let me see where I am. I'll start at the bottom here. Okay, I mean, we should know this, right? But when you react any metal, whether it's copper, magnesium, calcium, sodium, whatever, with an acid, any acid, doesn't matter what the acid is, any metal with any acid, the gas that's produced is always hydrogen. Okay, always. That was 5A. Um, sorry, I'm working backwards here, so people who asked you most recently are getting an advantage. 2A, 10. I did do this earlier because it was in the other booklet as well. So when you have acidic stuff, the crucial thing to mention is it reacts with the shells. You've got to mention that word reacts, okay? That's what the acid does. And then what do you think the reaction will do to the shell? You can say that it erodes it or it wears it away, something like that, right? You know, that's what you need to kind of say. It makes it sort of dissolve. Um, and then somebody asked 5B. Did I do 5B? Um, Two observations seen. Well, when you react to an acid with something, you generally see like bubbles, okay? And that would be one thing. That'd be easy an answer. And then what happens to the metal? So we've reacted some magnesium with an acid, right? So if I've got this magnesium inside this acid, what you will you'll see some bubbles. Yep, great, right? But gradually over time, what will happen is that this magnesium will disappear because it'll just vanish. So you can say it disappears. That's the other observation that you would see. Um, so I've done that. Just that's the question I just did, right? Yes, I did. Let me work backwards. 5B, yeah, 10. Question 7C. Did that already. Okay, so I did that earlier. So you'll have to just look back on that. Yeah, it's basically use what's it called? Universal indicator. And it'll turn purple with the stronger alkali and blue with the weaker alkali. Um, I think I've done everything, haven't I? Yeah, done everything anybody's asked me here. Right, I'm going to move on for time reasons. That is enough opportunity for you to ask loads of questions. Um, okay, which means I'll move on to this. So, those of you in year 11, again, this is beneficial for you, regardless of if you're in year 10, because you will have probably done some of this before. Um, so, we did quite a lot of different things on analytical chemistry. It's a bit of a weird topic. It comes near the end of chemistry. There's a lot of random stuff in there. So, these questions might be fairly random. But I will start with question number one, which you may not have covered in the lesson, to be entirely fair. So you probably know what chromatography is. It is when you kind of separate a mixture into the different things that are in it. And there is something called an RF value that you can calculate. The way you calculate an RF value is, so what happens during this chromatography thing? There's some water right here, and the water gradually soaks up the page and ends up finishing somewhere. And on the way, what it does is it basically takes some of the mixture with it. And depending on how far it's gone, you can figure out what it is. What you're supposed to do here is measure with a ruler, and this makes it slightly more complicated, the distance between here and here. Okay, now I'm going to tell you what this is because the problem with what we do sometimes is when we scale this down, ruler questions can sometimes go wrong. So you're supposed to measure this as being about 5.1 centimeters from there to there. Then you're supposed to use your ruler to measure from here to here, which is the full distance the water traveled. Now, according to what I'm reading, this is supposed to be 6.8 centimeters. But regardless of what two numbers you got, um, with those two numbers, you are then meant to divide the smaller number by the bigger number. So 5.1 divided by 6.8 is, according to the answer I'm reading, 0.75. That is what's called the RF value, that um, drug. Right, then there's more interpretation. What does the diagram show about drug D? Well, drug D, firstly, I could say that it seems to contain three different substances. That's why you get three different spots on this. But you also, because of what it's in line with, you can figure out a few other things about it. For example, drug D, another question, clearly contains um, drug B as well. It's got whatever this is. Do you see drug B went to there? So drug D contains whatever this is. So it contains drug B. So it's in line with that. It also um, contains one of the substances in E as well. You see that there? Because this splodge and this splodge are in line. That's what you're looking for, things that are in line with each other. So if we're looking at drug D, then it's definitely got something from B and it's got something from E. So that already gets you something else. And then you can say that it also contains this, which is not found in any of the other drugs. It's something unique to drug D. So that's how you get all of the, because there's quite a lot of marks in that question, right? So you have to kind of add a bit of detail. So effectively explain that in drug D, there is the same substance as drug B. There's also one of the substances in drug E there, and there is something that's not in any of the other drugs. That was how you go about doing that question. Um, yeah, so the measurements are fine. We will hopefully mark it right. But the reason you've got a different measure, you haven't done anything wrong, just to be clear. It's just that because we've cut this out of another page, we may have just scaled it up or down a little bit when we've made it fit in our booklet, and that changes the measurements a little bit, but you've still done it correctly. So don't worry. The point is you've done it correctly. It's just that ruler questions, and I found this in, I think, the test that some people did that had a magnification question on biology. Um, that doesn't always tie into the mark scheme because of the scaling of the page. Okay, so don't stress about that. Which substance is most soluble in the solvent used in the chromatogram? So the way you measure solubility is how, remember, solubility is the ability to dissolve in water. If something dissolves in the water, as the water travels up the page, it travels further with it. So because A has gone the furthest, um, it is the one that is the most, whatever the question is, um, soluble because it has traveled furthest up the page. Um, Similar or identical substance? That's a good question. Um, well, you can say it contains the same substance as in drug E or B, so the same. Symbol's the same, basically the same substance. One C on the bar. Sorry, I'm going to come to that. Sorry, I forgot about that. I will do that from the biology. I'll just get through um, this question first, and I'll just skip over to that one and get it done. This is going to be weird, these things. Which substances are, explain the result for F. What's going on with F? Oh, interesting. It didn't do anything. It did not move. Well, the only reason it doesn't move. Remember, what makes these things move is if they dissolve in the water. If they don't move, it's because they didn't dissolve in the water. So we explain that F has stayed on the line because it is insoluble or does not dissolve in water. That is how we would say that. I'm just going to skip over quickly to something from last week. Let me see what it was. Oh, that's strange. Why is it not already there? Um, so there was a question here in the biology. I appreciate I've suddenly switched over. If there's any more questions from the chemistry, please tell me, but then I want to do something else. Explain why the blood flow to skeletal muscle increases during exercise. Well, we should kind of know what if you're exercising, aren't your muscles working harder? What do they need more of if they are working harder? They need more energy. Okay, so during exercise, the muscles need more energy. How do they get more energy? They need more respiration to take place. That's what gives them the more energy. How does more respiration take place? Using more oxygen. And that's why more blood is sent to the muscles so that they can get more oxygen to be able to do more respiration, to be able to release more energy. That is the answer to that question. Um, what else? Do we have anybody got any more questions? Urgent. Shall we just keep going with this chemistry thing? What else did we have here? Was there anything at the end? Some weird questions at the end, but nobody's asked, so I'm not going to worry about it too much. Um, Potable is a word that means safe to drink. So that's the answer. That's okay. Potable water just means safe to drink. Just to be clear, a very common thing they want you to understand is the difference between this word and pure. You have probably never drunk any pure water in your life because most of the water we drink is has got other substances in it. It is not pure. That doesn't mean it's not safe to drink. It just means it's not only made up of H2O molecules. Um, so a common thing is understanding or testing you on the difference between those two things. So be prepared. Um, why should the water be filtered to make it potable? Well, what does filtering do generally? It helps to remove undissolved solid. That's quite important, that undissolved bit. Because when water is when stuff is dissolved in the water, filtering won't do anything to it because filtering only removes insoluble solids. Is it safer to have some? Are you asking me a specific question from somewhere? Um, is it safer to have high? I mean, no, it's neither safer nor unsafer. It is just the fact that it's hard to get pure water. We have stuff dissolved in the water that we drink. We just need it to be safe to drink, um, whatever else might be in it. 6C, let me skip over because I'm being asked. What does 6A say? Water is safe drinking. What do you call it? It's potable, obviously. Test for pure water is an interesting one. I'm just going to quickly talk about that. The test for pure water is understanding that if water is pure, it boils at 100 degrees. If it's not pure, it will boil at like 101 or 99 because it'll have other stuff in it. So the way you find out if water is pure is boil it, and the result should be is that it will boil at 100 degrees C if it is pure. And that takes us on to C. Describe a method to determine the mass of dissolved solids in a 100 centimeters cubed sample of river water. Okay, so first things first, we would get a container, okay, and weigh it because we need to put the water in something. Remember, if you want to weigh a liquid, you can't just dump it onto a scale. So you do need to specify that it's got to go into something. We're going to weigh the container firstly. It's quite important. And let's pretend, like I'm exaggerating the explanation here a little bit, but imagine that when we weighed it, it was 100 grams. Okay. Um, then what we would do is measure 100 centimeters cubed of water from this river. You can probably say using a measuring cylinder if you would like, right? And put it into the container. Okay, so we've now got a container which has got our liquid in. And we would now heat this up, okay, until all of the water evaporates. Okay, so heat it up until all of the water evaporates. And what's that going to do? Well, our container now, if there was any dissolved solids in the water, they will still be here because they don't evaporate. The water evaporates, and that leaves behind the dissolved solids in the container. And then you would weigh this again. And clearly, if let's say now that weighs 102 grams, a bit exaggerated again, then we know that the mass of the dissolved solids is the difference between what we had before and what we have now. It is 2 grams. And that gives us the mass of the dissolved solids. Um, I'll continue, yes, with question 6. A sample of river contains 125 milligrams per decimeters cubed of dissolved solids. Oh, this is a conversion question. Right. The key conversion is that there are 1,000. Oh God, right. Let me get this right. So there are 1,000 centimeters cubed in 1 dm cubed. That's the first complicated thing in that. So What it tells you is that in this sample of river water, this is how I do this question. Okay, I think it is quite a good way of doing it. The question wants it in grams as well. That's the other thing to look out for. Right, that there are 125 milligrams of something in 1 dm cubed of this water. Okay, when it says milligrams per dm cubed, it means one. When I say miles per hour, I mean this many miles in 1 hour. That's what I mean, right? So when it says per that, it means one of those. Now, one of those is um the question is calculate the mass in a 250 centimeters cubed. Okay, one of these, as I just explained here, because you need to know the conversion, is 1,000 centimeters cubed. So there are 125 milligrams of whatever this stuff is, this dissolved solids, in 1,000 centimeters cubed. It's the same. 1 dm cubed is 1,000 centimeters cubed. The question is, how many are there in 250 centimeters cubed? Now, 250 centimeters cubed is a quarter of this. So what I'm going to do is divide by 4 here, which means that this gets divided by 4 as well. Don't have a calculator with my phone. Um, So 125 divided by 4 means that in 250 centimeters cubed of this water, there is this much dissolved solids. I've just divided it by 4. Okay. Um, we still haven't answered the question because they want the answer in grams. We have to convert milligrams to grams now. There are 1,000 milligrams, 1,000 milligrams in 1 gram. So to turn this into grams, you would divide it by 1,000, and that would give you 0.03125. Yes, in 250 centimeters cubed of this substance. And to two significant figures, we're still not finished. It's got to be 0.031. That's why it's worth quite a lot of marks for that. So yes, that's how I would do that question. I think it just makes sense to me to write that down and do it almost like a maths little ratio thing. It's a bit like when you do those recipe questions in maths. It's sort of the same principle. We need this much to make one cookie, whatever. You see what I mean? Like, and you kind of just do a ratio and sort of figure it out from there. Can I do question 4, B, and C? I assume that's in the year 11 homework, so I will do that. Is that the rest of 6 done? Oh, no, there's E. I'll do this one as well. A water company, oh, God, allows a maximum of 500 milligrams per dm cubed of sulfate ion in drinking water. A sample contains 44 milligrams per dm cubed. Um, isn't this the 44 divided by 500? Calculate the percentage of the maximum allowed mass of sulfate ions in the sample of drinking water. I think this is just this number divided by this number times 100. You basically turn it like, so we're saying that calculate the percent of the maximum allowed mass. The maximum allowed mass is 500 in the sample of drinking water, which is 44. 44 over 500, which is 44 divided by 5. I do this in my head. 4.4, 8.8, the answer to this question. It is 8.8%. 8.8% is the answer to that question. So you're basically just turning this into a percentage. Do that divided by that divided by times 100. 4B and C, again, I assume this is the year 11 one, but please tell me if not. So question 4 gives you a test for hydrogen, which is the squeaky pop test. This half equation shows technically what we call I did this with electrolysis recently. Remember, oil rig reduction is gain of electrons. So you just put reduction, and because it's the gain of electrons, the easiest answer to that question. Then there is a calculation question, which I'm not going to do for now, but it's because nobody's asked. Bronze medals are made from an alloy of copper. Copper can be extracted by phytomining. Why is phytomining used to extract copper? Well, it it's only 1 mark. It is cheaper. Let me see what the mark scheme says. Um, More economical than other methods. So the reason for this is that we use this process mainly because it allows us to extract copper from low-grade ores. That's the best answer, if you would like the best answer. we use this process because the traditional way of extracting copper is electrolysis or mining, and that uses, that damages the environment and it uses loads of energy. This process allows us to get copper without using too much energy. And it allows us to get copper from a low grade ore. That means like a rock which has only a little bit of copper in it. Um, the main steps in the phytomining process. So phytomining, the way I remember this, there's two processes that you need to know, certainly for AQA, bioleaching and phytomining. I remember this as phytomining involves plants because it starts with the letter P. Bioleaching involves bacteria. It starts with the letter B. The process of phytomining involves plants grown in soil containing copper. Okay. Then what we do, or what happens is when they are grown in soil containing copper, the plants basically absorb the copper ions, or just absorb the copper. I think that should be enough. And then what we do is we sort of harvest them and pick off those plants, and then weirdly we burn the plants to make ash, and that ash now contains the copper compounds. Sorry, the copper ions or comp ions. Copper's fine. And then we don't have to say any more. But what actually then happens is we use electrolysis or displacement reactions to get it out. But that is the process of phytomining. And that covers question 5. Any more? Shall I just keep doing some other ones? Um, I'll do this because it's a kind of, even though we didn't do this, I think we have a lesson on quantitative chemistry with everybody very soon because it's always horrible. But I will just tell you how you go about doing this question because you wouldn't have done this definitely in the lesson. So I think it's important to just give you some information. The question says 0.72 grams of magnesium reacted completely with hydrochloric acid. The equation is there. The question is calculate the mass of magnesium chloride produced. I always do this in these questions. I write down the um what's the word I'm looking for? The formulas that are relevant to the question. The question is, if I start with some magnesium, how much of this do I get? The rest of this is not relevant to me in terms of this calculation. And so what I then do is write down how much of one of these I'm starting with, which the question will tell you, 0.72 grams. The question is, how much of this will I produce in the end? When we do chemistry calculations, we cannot use grams to do any actual proper calculations. We have to convert the grams to something called moles. The number of moles is calculated by taking the mass in grams and dividing it by the MR, which is the top number on the periodic table, the mass number of the substance, or if it's a compound, it's the formula mass, which we add up and work out. So the way I present these questions, and for those of you in year 11, we will do a lot more of these, and you will see me present this in the same way every time. I have the mass in grams. I need to divide that by the MR. For magnesium, they tell you in the question it is 24. Okay, I'm going to get my calculator open now. And I want to divide that. That will convert these grams into moles, and I'll get 0.03 moles. Right, then we look at the equation because what the balanced chemical equation tells us is a ratio of the moles of all of these substances. Now, because there's a 1 there and a 1 there, or nothing there, which means there's ones, it means that however many moles of this I start with, I produce the same number of moles there. If that had been a 2, then I would double that. But in this case, it's just 1 and 1, which means that if I start with this many moles here, I'm going to produce exactly the same number of moles there. So that's turned that into moles. I now know how many moles of magnesium chloride I'm going to produce, but I don't want to know it in moles. I want to know it in grams. And therefore, I need to go back to this equation and remember that to turn moles back into grams, you multiply these two things together. So the MR of magnesium chloride is magnesium, which is 24, plus 2 chlorines, which is 2 lots of 35.5, which is 95. And what I do then is times those two together to convert my 0.03 moles back into grams. And it gives me 2.85. And hopefully that is the answer if I just check. 2.85. If you do enough of these, it becomes very repetitive, I promise you. But um, you haven't done loads of them. So once you do loads of them, you will find that it is quite consistent every time in terms of what you have to do. Right, anything else that's exciting here? Test for hydrogen gas. I did. Let's have a look at what was at the end of this because these are all quite new to me. Um, yeah, how to do a flame test. You might not have got to with the lesson. In fact, no, I won't do that one. I will do these gases. There's a gas question here that's really good. Okay. So the reason this is a good question for me to just explain here, because it links many things together, and that's what I like to try and do to make your lives easier. You connect the dots with lots of different topics across the sciences and possibly maths in some cases. This question is about gases. Figure 16 shows the relative amounts of three gases in the early atmosphere compared to the composition of today's atmosphere. So you are meant to know that when the Earth was formed, whenever that was, there was a large amount of water vapor in the air, a large amount of carbon dioxide in the air, very little oxygen in the air. Now we have quite a lot of oxygen, a lot less water vapor, and a lot less carbon dioxide. You see how they have decreased loads and that has increased loads. And you need to know essentially how this has happened. Okay, that's more or less it. And you can get a very big question like this, effectively asking you, explain what has just happened here. Why have we gone from having loads of water vapor and to virtually none, loads of carbon dioxide to virtually none, and no oxygen to loads of oxygen? That's essentially what you have to be able to explain. So let me explain the sequence of events that you want to be able to explain. First of all, um, let me just give you just a backstory firstly. Why was there so much carbon dioxide in the Earth's atmosphere ages ago? Mainly because of volcanic activity. Volcanoes erupting release loads of carbon dioxide and water vapor, actually. And also, the Earth was generally quite hot at the time. And when it's quite hot, then any water that there is evaporates and is water vapor. Then the way you start answering this question is by first explaining that the Earth cooled. What does cooling do to that water vapor? It makes it condense. Okay, so the water vapor condensed, and it became a liquid. Where did all that liquid go? It is still here. It is what we now refer to as seas and oceans. Okay, so that's how you begin to explain what's begun to change. Okay, so all that water vapor is basically it's still here technically. It's just not in gas form anymore. It's in liquid form because the Earth is cooler than it was before. Right, then we can start to explain what happened to the carbon dioxide. Carbon dioxide can dissolve in water. So once there was water, the oceans, a lot of the carbon dioxide dissolved in the ocean. And that began to reduce the amount of carbon dioxide. And some of that carbon actually became part of the shells and bones of the sea creatures, and it kind of still is in there. It's just not in the air anymore. What else can we say? Well, um, how else can carbon dioxide go down and oxygen go up? Photosynthesis. So we now need to explain that plants evolved. Plants do something called photosynthesis, in which they take in carbon dioxide and they release oxygen. So the amount of carbon dioxide started to go down and the amount of oxygen started to go up, which goes a long way to explaining what is happening here. Have we got a question? Um, Dissolved into marine life is probably a jump, right? So what you kind of probably want to say is that it dissolved in the oceans first, and then some of it became part of the marine life, or you want to be specific about the shells, because that's kind of where it goes. Um, and then also, if you want to take things a bit further, so a lot of these plants have now got, because they've taken in carbon dioxide, a lot of carbon in them. Okay, and so have the marine life that's in the sea, right? They've got a lot of carbon in them. What eventually happens to everything? We all die, right? When we die, we end up in the ground, and we effectively, dead plants and animals become fossil fuels. And that carbon that was all in the air ages ago effectively is locked up in the fossil fuels over time, right? So even if we say it dissolved into marine life or went into the plants and animals that are in the sea now, effectively everything still dies. And so it kind of ends up in the ground and becomes, as we know, fossil fuels. Because if I said to you, what are fossil fuels? They are the remains of dead plants and animals buried underground over millions of years. And so if it wasn't for humans, just to be clear, all of the CO2 that was originally in the atmosphere would stay effectively locked up in the in these fossil fuels. But what do? We dig up those fossil fuels and we burn them. And when we burn them, what happens? That CO2 that was originally in the air, which ended up in all of those animals and underground, gets released back into the air, into the environment. And so that is what's gradually adding carbon. We finished the question, by the way. I'm just adding more, but gradually has increased the amount of carbon dioxide that is in the air because we're burning fossil fuels. What else are we doing that's affecting the amount of carbon dioxide? Deforestation. We are cutting down trees. And what that obviously reduces the amount of photosynthesis that is going on, which further adds carbon dioxide into the atmosphere. So this all connects together into different areas of your science knowledge, okay? Whether it's photosynthesis or this stuff in biology, or, even though it's technically a chemistry topic, it is important to be able to link these things together, which is what I can do for you. Um, Anything else that's exciting over here? Oh, and also, just so you know, everything I just said, pretty much, with some slight additions, is part of the carbon cycle, which you learn in biology. The carbon cycle involves the CO2 going into the plants from photosynthesis, the plants dying, um, and becoming fossil fuels, the burning of fossil fuels, releasing that carbon back into the air, decay, releasing carbon dioxide back into the air because bacteria and so on respire. So this is all so connected together that having a good understanding of this really does help. What's going on here? The sentence is about one possible theory of how the Earth's atmosphere evolved. Write the letters in the box show the order of the sentences. So has come first. Volcanoes released water vapor and carbon dioxide. Yes, they did. Okay. Um, I would suspect the Earth cooled will probably come next. Water vapor condensed to form the oceans. Then carbon dioxide dissolved. This is basically repeating the previous answer, virtually all here. It dissolved in the ocean. Carbon dioxide dissolved in the oceans. Then what happened? Plants evolved, probably. Plants evolved and used photosynthesis to take in carbon dioxide and make oxygen. And now the carbon cycle keeps the composition of the atmosphere almost constant. The difference is that we're making it worse by burning lots of fossil fuels. But if it wasn't for us, there would be a perfect carbon cycle going on where plants would take in carbon dioxide, they would die, then they would decay, and that would release a bit of CO2 back into the air, and then they would take it in. So we would have quite a perfect carbon cycle. The problem is that we're also burning fossil fuels that's adding CO2 to the environment. Um, Greenhouse gases. Yeah, I'd love to. We do that now. Oh, I need to do that math question as well. So I'll do this last, and then I'll just move over to a math question that has been asked. I might not be able to do one of them. I can't figure out one of them immediately. I need a bit of time for that one, but one of them is really easy. So, greenhouse gases. So, firstly, effectively, the main greenhouse gas is carbon dioxide. I say the main because there are other greenhouse gases like methane and water vapor are technically greenhouse gases, but the main one is carbon dioxide. Now, I suppose the question that you're asking is what is the point? Why do we call them greenhouse gases? It is because of the following. This is the Earth, and we are on it. Okay. Now, this is the sun. What happens, or what used to happen at least, is that heat, the sun's heat would come in. Okay, and I'm going to explain this in much more detail in a moment, but the heat would come in, the Earth would get warm, What do hot objects do? They give off heat, right? My hot cup of coffee gives off heat. And so overall, what the net effect of this would be zero. Like it would heat something up, but then it would cool down, heat something up, cool down. So we would kind of be where we are. However, as a result of us burning fossil fuels and cutting down trees, there has been an increase in the amount of these kind of gases, ignore the water vapor, these kinds of gases in the air, right? Because cutting down trees increases carbon dioxide, burning fossil fuels increases carbon dioxide. We've now got this layer of greenhouse gases above us, and they do something special. So I need to go into a bit more detail now. When and this links to physics as well, this is why everything's so intertwined. The sun emits radiation. The radiation that the sun emits is mostly ultraviolet, or a lot of it is ultraviolet. From physics, you are meant to know that ultraviolet waves have a very short wavelength. So I'm drawing these waves very deliberately as quite close together, as you can see that, quite close together. And what this short wavelength does is it allows these to pass through that layer of gases that is above us. Okay, a short wavelength waves generally have more energy. They can travel through substances more easily. When these waves hit the Earth absorbs their energy and gets hot. It's very similar to the water in the microwave. It absorbs the heat from the wave, and the Earth gets hot. Now, when the Earth gets hot, gradually it then emits heat as well, right? Just like my hot cup of coffee, as I explained a minute ago. But when it emits um, heat. Heat waves or heat radiation is a different wavelength to ultraviolet radiation. It is slightly longer. So as you can see, these waves that I just drew are further apart. As you can see, they're further apart than they are here. So this is longer wavelength radiation. This is short wavelength radiation. And the key difference between the short and the long is that the long wavelength radiation gets absorbed here. It doesn't leave and go away from the Earth. It gets absorbed here and ends up staying here. Okay, so that heat energy gets re-radiated back to the Earth, causing it to gradually heat up, which is what global warming is. So this process of these waves being absorbed is called the greenhouse effect. The consequence of that greenhouse effect is the Earth getting hotter and leading to global warming. It is critical that you understand this in terms of short wavelength waves coming in from the sun and longer wavelength waves trying to get out, but then getting trapped by these greenhouse gases. That's really important. It's not as simple as just heat in and then gets trapped on the way out. A lot of times when I ask people this question, they say, oh, it's when the sun's heat gets trapped or something vague like that. But that isn't quite precise enough. You need to understand it in terms of the different wavelengths that are going on. Right, that is the greenhouse effect. Last question. I'm going to do one of the questions that was sent to me. There's one of these that I need to think about for longer, by the way, which is I can't believe you would get asked this question about the locus of P has that following property. That to me that doesn't seem likely as a GCSE math question. Um, but I'll definitely do the other one quickly. Um, okay. Do some waves pass through and don't get trapped? Yes, but some of them do get trapped on the way out, and that's the. But if it heat radiation, most of it, a lot of it will get trapped. Yes, not all of it, but the point is but more of it is getting trapped because there's more carbon dioxide. That's the crucial point is that because we're burning fossil fuels, we're adding to these greenhouse gases, so more of it is being absorbed than it was if we weren't doing this. And so we're heating up the Earth. That's essentially the point of that. Right. So lastly, somebody has sent me a math question, so I'm just going to do that question, which I'm just going to do one of these, okay, rather than the second. I'd have to figure out the second one. It'll take me a while. So this is, I mean, it's really easy, one of them. Okay, did not work. Okay, oh, I missed out the first bit. I missed out the important part of that question. Sorry. The test for pure water, I'm going to repeat it. The test for pure water is that you boil it, and if it boils at 100 degrees, it is pure. That's it. Water that isn't pure will not boil at exactly 100 degrees. It will boil slightly off it because it's got other impurities in it that affect its boiling point slightly. But if it's pure, it will boil at 100 degrees. Right, here is a graph in maths. The question that I want to answer just very quickly is the coordinates of P. What do we know about this coordinate? We know that it is definitely zero something, right? We know it is zero something. Um, and we have an equation. Um, and Q as well, okay. The waves the Earth emits, should I call them heat waves or UV waves? Emits is the heat waves. The UV waves are the ones that are coming in. So the UV waves are coming in and the heat waves are going out. But I think it's better to phrase it as short wavelength waves coming in and long wavelength waves going out. You can name them. It's infrared is the proper word for heat waves, but I think it's easier to do that. So P and Q, right. Okay, Q is going to be slightly more complicated. Uh, is it? Possibly. I mean, there's so many ways to do this. I'm trying to find the GCSE way to do it. Anyway, P is easy because I know it's zero something. All you do is take that zero and sub it into where the x is in this equation. So it becomes 25 minus 0 minus 8, which is minus 8 squared over 4. Um, so minus 8 is 60 squared is 64. So it's 64 over 4. 25 minus that doesn't make sense. Oh, yes, it does. Sorry. 64 over 4 is 16. 25 minus 16 is 9, which means that this coordinate is 0, 9. And then the coordinates of Q. See, the thing is, there's two ways to do this. I'm trying to do it the way that's most likely to be the question. So that is actually the same as 25 minus a quarter x minus 8 squared. I can tell you the answer. It's difficult to explain it quickly, but the answer to this question should be 825 because it's basically completing the square. So if I complete the square, okay, so if I've got an equation like that, right, one of the benefits of completing the square is it basically immediately tells you where the graph turns because that's the opposite of this is the x coordinate of where it turns, and this is the y coordinate of where it turns. And then the number here is irrelevant. It doesn't do anything. Um, so that's the answer. So that's what you need to look out for. That's the x coordinate of a turning point, and that's basically the y coordinate of the turning point. So it should be 825. Right. I will have a look at that other question that you sent, but it's going to take ages. 6D on the year 11. I think I might have already done it. Yes, I did. I would recommend that when I end this meeting in a second, you within about half an hour, a video will appear on YouTube. If you look sort of three-quarters of the way through that video, you will find me explaining this question. But that is the answer to it at the bottom there. But I would recommend you do that. And if you're unsure how to find that, then just contact us and I'll tell you. YouTube is where all of these things end up. Straight after, not straight after, but it takes a little while, so it will end up there. Right, I think that's it for today. Any other questions, please feel free to send, and I will see some of you